I think I forgot to tell you that we'll have another class exercise right today. Don't worry about it. It's good to have many because then each one of them is not as important. And that's how I justify things. And then also I dropped the lowest grade, so don't worry too much. And this one is a short one. And then I kind of, to make sure that I don't forget, gave you heads up for the next one when it's going to be. I know that Tom and Valerie, you are probably away, but we'll arrange for that. We have done this before for Tony, and that's not a problem. Okay, so continuing our discussion, we did some examples on area stress function in Cartesian coordinate system, and we looked at polynomial form. So it was power series, and you have homework problem. So I want to spend just one class without going through too much details on one other form of the solution that you may have in Cartesian coordinate system still. And that is through separation of variables, another method. Before doing that, I want you to think why we would need another form. Now we learned very well what to do when it is power series, polynomials, so why bother with some other form of solution? So as I'm writing that, think about it, and I like to have a discussion on that. So what we were doing is we are trying to look at the different solutions to biharmonic equation, and we looked at polynomial solutions, polynomial form, right? And then today I want to look at some other form and a method which is separation of variables, or Fourier method. Sometimes people like to do that. And if I haven't said this, we are looking at the materials in chapter 8 here. Okay, so we are done with that. So my question for you is, why bother? Why looking at some other forms of area stress function if we know how to solve the problem assuming that area stress function is polynomial? Let me help you. When you assume that the stress field phi is polynomial, what kind of a stress potential phi, when you assume that it's polynomial, what kind of a stress field did we get always in terms of the kind of function? Yeah, because you make derivatives. So can you say that you can solve all the problems in elasticity using polynomial stress fields? Are the solutions always polynomial? No. So that should give you enough reason to listen to what is going on today, which is a lot more general solution, but also, as you will see, a lot more complicated, and that's why we cannot do a lot of it in the class. But it's very important that you get familiar with that, because polynomial solutions are not general. It's only good when the stress field can be expressed using a polynomial function. Okay, now that hopefully everyone is convinced, let's get started. I first have to do a very brief review of how you would solve an ordinary differential equation. Let's see if you remember, but if you don't, that's not a problem. We just quickly look at it. So remember, if you have a linear homogeneous ordinary differential equation with constant coefficient, which has a form like this, this number in parentheses is of course the order of the derivative. Yn plus a1 yn minus 1 all the way to a constant. So maybe I should have written a quick review of a special type of ordinary differential equations. It's linear, as you can see, homogeneous. The other side is 0, constant coefficients. So if we take y to be a function of x and the ai to be real valued constants, how did we solve an equation like that? How did you solve this? So the review seems to be necessary, right? We forgot about it, and it's because, remember what I told you before about differential equations? The solution somewhat appear and makes you very uncomfortable, but it's because people have worked on it for a long time. So now if I write it down, you all remember. So we considered exponential solutions, right? So if you consider a solution, an exponential solution, it's actually one of the easiest differential equations to solve. Consider a solution of the form, and now you will all remember. Yeah, you substitute this into the differential equation, and what do we get? A characteristic equation, right? You have heard this term before, I'm 100% sure. The so-called characteristic equation is going to be something like that. You can easily see y alpha n plus a1 alpha n minus 1 plus an times, and for this basically if you substitute you get that, and the characteristic equation is basically this part, right? Because this has to be equal to 0 for any value of x. I'm going very fast because I know this is something you are familiar with. And how many roots in general do we find when we have a polynomial of the order n? N. But these n includes complex valued and repeated roots, right? So let's write this down, because this is where actually it's important for developing the biharmonic equation. So we find n complex roots if you consider real numbers to be a special case of complex numbers, then you can say that we find n complex roots for alpha, which may be repeated. So we have alpha 1, alpha 2. So if you don't have any repetition, the general solution, how do you obtain that? Do you remember? It's the simplest case. If all the roots are distinct, then how do you form the general solution?
Linear combination.
Exactly, a linear combination of everything. So you have a constant times each root and you sum them up. But things become a little bit tricky if you have multiplicity. So what happens if, so suppose that one root has a certain order of multiplicity. So suppose alpha sub k, one of these roots, has multiplicity m, which should be less than, no, not much less, less than or equal to n, like an integer. Then what is the magic solution? Then how do you build up the extra functions you need? You cannot just say, oh well, they are all equal, then I just, they all be equal. So you need to have n different solutions to make the general solution. What is the magic, Gerald?
You multiply each term by, in this case, x. This would be, I guess, however.
Perfect. It's in the right direction. So exactly. So then, if this happens, then a function which looks like that, exactly, you multiply x by e to the power of alpha k, that's what we assume, times x. But this, it doesn't have to be x, right? It can be x, x squared, x cubed, until xp, where p can go all the way to m minus 1. You have seen this before, so I'm sure that this is ringing some bells. And Gerald is a proof that you have seen this somewhere. Okay. So then everything is okay. Then you just build these solutions, and again, linear combination will be the solution. Okay. Perfect. Just for the sake of completeness, I write that, I know you all know that the general solution will be a linear combination. And we have defined linear combination very early on. If I mark this with an asterisk of solutions like this one. Okay, that's all the review I wanted to do. Now let's go back to biharmonic equation. Any questions about this? Prabha? Was it too fast? You wanted to write? Okay, sorry. I pick on Prabha, as you know, because he's my student and I like him. So this is the information I wanted you to have fresh in your mind now that we discuss. And I'm going to skip a lot of derivations today, so don't worry about derivations too much, but I want to communicate the basic things about this solution, because if you decide to read the book, and if I don't do that, I believe you wouldn't understand what's going on. Okay, so now let's go back to biharmonic equation and the solution that I promised we are going to look here. So biharmonic equation solution. So I said that we are going to do separation of variables. What does it mean? Biharmonic equation is a stress potential, you can think about it, a stress potential field which can be a function of x and y. When I say separation of variables, it means that I take it to be, so it is a function of x and y. I take it to be a multiplication of a function which is strictly a function of x and a function y which is a function of y. And in particular, we consider this form, not any x and y, at least not this in this class. We consider exponential function. And this is not a bad idea, because if you have a very general loading condition, you can always use Fourier series or Fourier integral to study each exponential component, each part of it, and then sum everything up, superimpose to get the general solution. If what I just said looks very foreign to you, don't worry about it. At the end, I try to explain it to you. If you are familiar with Fourier series and integral, I think maybe you understood a little bit of what I'm talking about. So choosing the exponential form is a very general form. That's what I want to convince you. So now, if we substitute this in the biharmonic equation, we get a very simple equation. So when we want to see if this satisfies biharmonic equation or not, we substitute let's call it like with a star in biharmonic and this gives us if we do that, so just like before, if you want to make sure that this is a solution for all x and y, what we want to ensure that it would be equal to 0 is this part. So that becomes the characteristic equation. So if you look at this equation, then what are the roots? Yeah, but generally. Right? So, now, Tom said 0. Let's consider two cases. So if we have alpha equal to beta equal to 0, and then we have a case where this is the relationship, and they're not necessarily zero. In the first case, what is the order of multiplicity of the roots?
4.
4, right? In the second case,
2.
exactly. So we have multiplicity. Multiplicity. So what does that mean? So if you want to write the general solution, how would that look like? Going back to what I told you about multiplicity, try to write a general solution to see how it would look like on your own first. How does it look like? So obviously this is what we started off with, but I have to add some other things to it, right? I have to add some x and y, and they have to have some powers gamma, and what did I use here? Delta. And if I'm thinking about alpha is equal to beta equal to 0, these exponents can go up to 3. If I'm thinking about the non-zero case, they can go up to 1, can be 0 and 1, right? Now, I'm not going to go through the derivation because it's going to be very long. If you are very interested, I have it written up. I can show you, give you a copy, but I'm going to give you the solutions. So this is how it looks like. So if you look at the case where alpha and beta are equal to 0, the general solution for that case is going to be, maybe I color code this because I don't want to write it 2 times and then sum the things up because they are very long. So the solution which comes out of the case alpha equal to beta equal to 0, you expected it to have terms with x cubed and y cubed the most. This is what we expect. So it looks like something like that. No, I shouldn't make, sorry. So the phi, I shouldn't make that purple. I don't think so. Just this part, which is related to that. So I just use k. So it's like k0 plus, you have to be patient, k1x plus k2 x2 plus k3 x3. And you may wonder where is the exponential, because alpha and beta, where they are equal to 0, exponentials become 1. So there is no exponential. Plus k4 equal to y times y plus k5 xy plus k6 x squared y plus k7 x cubed y plus k8 y squared plus k9 x y squared plus k10 y squared, is it y squared 2 times? Should be an error here. Plus k11, let me check that, x y cube. Yeah, that's what I just realized. It is y cube. So it's k10 y cube plus k11 xy cube. Let me check everything one more time, because your book has actually an error, which is obvious why this can happen, right? Because there are so many. So I want you to have the good solutions: xy squared, k10 y cube. This is, I made a mistake here, k11 xy cube. That's it. So now for the second part, so this you have to sum it up with the solution from the second part, which I make green. But I hope you see what I'm doing. Is this clear what I'm doing? So I'm not writing things separately because there is no point of writing this again. And there we have, then you start to see the exponential. So now this is coming from these solutions, e I beta x, and now we have some other constants. So c1 e beta y, c2 e minus beta y. So you also realize that when you change the sign, because we have alpha squared plus beta squared, if alpha is in the solution, you have the same solution with negative alpha. So beta, negative beta. That's why you see this symmetry. Plus c3 y e beta y plus c4 y e minus beta y plus c5 x, now x e beta y plus, I wish it fits here, c6 x e minus beta y, and of course this is the last one. And then kind of similar terms here. C8, C9, y e beta y. So now you see why I didn't want to have the derivation in the class. E minus beta y plus C11 x e beta y plus C12 x e minus beta y. So it's a good thing that the solution is so large, because that means that depending on the physical problem, then you can examine it and choose a good part of it, because this is all going to satisfy the biharmonic equation, and then you can develop the solution. And this is what we are going to do in polar coordinates. So you will see how from the big ugly solutions you actually can get very nice elegant solutions for specific problems. So don't worry too much about it. Now I'm not going to write it down, but sometimes you see this solution with sine and cosine, and the way you can go from this form to sine and cosine is to use these relationships from, for example, Euler's formula. So I just write this down here in case you see a solution and you don't know where those are coming from. So if you take the solution and you use these identities, which I believe you are familiar with, then you may see the solution in So in the book, you will see that the solution has these terms, but some of the terms are missing. So be careful about that. But I'm not going to write it. So if you substitute for the exponential in terms of sines and cosines, then the form could look a little bit different, but that's where it is coming from. I guess there is really no need to write that other form in this class. I skip that. If you are interested, let me know. I can send you the form. Now, what I want to do is to solve one, I would call a very interesting problem, which has a solution which is kind of a part of this solution. That's kind of the only manageable example that we can have in the class, and I think it's quite interesting. So it's a very interesting problem to look into, and you will see why in a matter of minutes. Any questions about how we got here to this solution, etc.? Okay, so example. This example is quite interesting. Needs some patience. It's not everything is as easy as the polynomial solutions, but it's quite interesting. So consider a case of a plane This is from Timoshenko book, actually. So here is the x-axis, and here is the y-axis. And this plate has a thickness which is 2h, and we don't really care about the other end, so that's kind of, we don't care about the right end, and you will see why later on. And let's consider a non-polynomial stress potential function, which is kind of from this family of solutions I showed you, but a very simple one. And this looks like that. If a and b are constants, is e to the power of minus bx over h, and then times c cosine byh plus by over h sine by over h. So, as I told you, when you see a general solution, as you have seen in the polynomial form, remember the form is very large, but the examples we solved were only like one component, two components, right? They are not going to be very big. So you always use a solution which fits a particular problem. Now, accept that you can try it, and I really suggest that you guys use MATLAB or Mathematica. Does everyone here know how to use MATLAB or Mathematica to calculate derivatives, etc.? Because you are going to, you need to do that from now on. Things are getting a little bit, not as simple as before.
So derivatives as in numerical?
No, more. This is like a syntax kind of thing in MATLAB and Mathematica. Maple, I don't know if anyone uses Maple still. It's like dead, but something like that you can do. If you have a very fancy calculator, it even does that, but it's so hard to put things in. I find it very hard. Okay, now this is so you all agree that this is kind of a form. It's a small function from the second group of function. Now, and accept from me, without wanting me to prove this, please, that it's a solution to biharmonic equation. Okay. Now, if you calculate the stress field, so remember the relationship between, we are still in Cartesian coordinate system. It looks like that. XY is right. So if we do these calculations, here we get something like this. So a b squared, the exponential form stays over h cubed, and then we have negative 2 plus c h cosine by over h plus by sine by over h. And this one is plus ab squared this is not yet too bad, but when things get too bad, I'll bring you the equations so we don't need to write them. But this is kind of a fun problem to look at. You will see. Just be patient and trust me for now that this is going to be good. So when I say to use MATLAB or a Mathematica or whatever tool you are using, is if you give the function, then you can calculate these derivatives without actually calculating them by hand, because it's easy to make mistakes. Okay, so what did we do before? We looked at the boundary conditions. So it's the same here. So let's look at the boundary conditions of this problem. So let's call, I have this boundary, and then I have this, and I have this. So what happens when, yes, please.
Sorry, can you go back up? I didn't see what
Of course.
boundaries were labeled as one.
Oh, sorry. Top 1, then bottom 2, and left 3. Be patient. It's going to be very interesting. I promise you that it's going to be very interesting. So interesting is a subjective. I realize that, and it's late, and but it's really interesting, right? How would you describe the top part? It's x. Imagine that this is going to go. We don't care. X is just greater than equal to 0, and y is equal to h. And then, like always, we look at the n vector, which would be just j, right? So you have 0 and 1 basically for nx and ny. And then what we did before was I've shown you how to calculate the traction tx and ty. So if you allow me, I don't write the equation, the Cauchy, and I just write what would you get for tx and ty. Is that okay for everyone? So if I do that, so let me just write the Cauchy law here very quickly, right? We have done enough of this, right? So if we do that, and if you equate y equal to h, we get tx. Of course, this doesn't look very good, but it's important to write it, as you will see in a second. I'm trying my best to make this enjoyable, but there is a limit to, yeah, so it's looking rather complicated compared to what we have seen so far. So this one, so C, and I don't think I wrote it down, but this A and B and C, they are constants. And very similarly for number 2, for the second boundary, which is the bottom. So it's the same x, but y is equal minus h, n is what? Yeah, just to see everyone is still with me. And remember that here I have substituted y equal to h. That's why instead of by over h, you just see b or something like that in the equation. So here tx will be very similar looking. And ty very similar to the above. Okay. Now we can start looking at things. Does it look any better? No, not really. It looks very complicated. But I want you to observe something here. Now, if the top and bottom are traction free, what conditions should be satisfied? Tx and ty have to be 0, right? You agree? Look at the both boundary number 1 and 2. The exponential cannot be 0 for all x. This is not possible. So what has to be 0 is what is in the parentheses. Isn't that the same for both boundaries? So what I want you to see from these equations is that if the traction on the top is 0, it's also 0 at the bottom. So the same conditions which make the top traction free, it makes the bottom of this domain also traction free. Okay, and what are these conditions? So if I call it number 1 and 2, b cosine, this is what is in the parentheses. If this is equal to 0, what is in the parentheses, and the other one, c cosine b plus b sine b is equal to 0, then both 1 and 2 are traction free. So it turns out that if we combine 1 and 2 again, we get an equation like 2b plus, because at the bottom you can write c as a function of b. Let me do that because this part is easy. If the cosine is not 0, I don't write this very mathematically correct. If the cosine is not 0, you can write that. And then if you substitute c up, you get this equation, 2b plus sine 2b equal to 0. Okay. Does this equation have any roots? X plus sine x equal to 0. No, it doesn't. It has only, it only has complex roots. It does have roots, but they are not real roots. So it's complex roots. So keep this in mind. Now, this is like a suspense. Now, we need a last piece of puzzle. We didn't do anything about the left side, the boundary on the left side, boundary number 3. Let's look at that too. So everyone remembers this equation, 2b plus sine 2b equal to 0. Now if you look at boundary number 3, what can we say about this boundary? What is the way we define the problem? This is x equal to 0, y between h and negative h. And so x is equal to 0, y between, and how about n? Exactly, negative Rn. So now if we write tx and ty, if we actually get, I skip one step because I want to get to the point of why I'm solving this for you. If we get tx and ty, it's not that interesting. What is interesting is that if you calculate t, if you calculate the integral over the left hand side. So if you do that for tx, you are going to get when I'm calculating the integral, what I'm actually calculating, what did we call this last time? Oh, I don't hear you. Yeah, what am I doing when I say I'm calculating the integral over the left-hand side? Yeah, it's a resultant reaction. So it turns out that if you calculate the resultant of tx, this is how it looks like. If you calculate the ty, it is 0. I didn't write tx and ty because it's large and that's not the point. This is the point. Now, take a little bit closer look to this equation for the integral of tx and compare it to what we had before for 1 and 2. What do you see? Yeah, in the parentheses, this mysterious expression is the same. So what can you say? Like if the top and bottom are traction free, this is also going to be 0. Does this make sense? Okay. So if So the traction on the left end has a zero resultant. I promised you something interesting, and so far you are probably disappointed. Yes. I'm sorry. No, so if top and I'm not sure I'm understanding. So so that's what I'm saying. I didn't write the fraction. You want the equation?
Go to the left side.
No, let's go back. So that kind of that's a common problem when you look at these solutions. Remember, we start with a solution, we find a problem. So if I didn't draw anything here, that doesn't automatically mean this is fraction free. I have phi. Yeah, so that's typical. So remember what we did last time? I'm doing exactly the same thing. I brought this phi at you. Like, here is phi. This is Timoshenko. It's not my fault. He is saying that this is a phi, and let's see what kind of problem does it describe. It is always like that. This is kind of what we said, inverse method of solution. Is this conversation clear to everyone? This is a general problem with area stress function solution. It's hard for students to understand because what you are used to always is to get a problem with the forces on it and then you get a solution. Here is you get a domain, a stress potential. That's the best physical meaning I can think of for area stress function. And then you try to find the problem that you can solve in that domain with that solution. It's a kind of a interesting, like a strange, but it's like differential equation. You never question that.
So let's go to where integral yes. The first integral, we are integrating fraction Tx along y. So why do we go to 0? Is it not because the left side is
I'm just telling you that if you calculate Tx and Ty, I have the expressions. They are not equal to 0. But if you integrate it over the left end, Ty automatically will be 0. This integral will be 0. And Tx, it will look like that.
Yeah, this should be a resultant force on the left side.
There should be, there isn't.
Yes, there isn't. So that's what I'm saying. So there is the density equal to 0 because there isn't.
Yeah, there is no resultant traction on the left hand side.
Yeah, that means it's equal to 0.
Yeah. It's not. Exactly. I have a lot of people helping me to teach. It's great. No, it is actually great that we have this discussion. Exactly. Do I have to explain that?
I'm trying to match what is on that.
No, it's good to discuss it. It's good to discuss it because this is actually what is important and it's interesting. This is quite interesting and we are almost there. Okay, yes, Gerard. I didn't hear. Gerard, I didn't hear. Sorry, I missed the joke. Yeah. So remember how, for example, if you have this situation, the resultant force is 0. But does it mean that this is traction free? So I just wanted to say that, and Tom said for me, Prabha helped. No, that's great. No, who was this? Was Zach helping someone else the other day? So it's great. So that's what you want to see.
So it's kind of arbitrary at this stage.
Yeah, and this is the main thing of me solving this problem. This can be, and for this problem, I didn't even specify it. So here we had to say this is linear. Here I'm saying, I don't know, this is some traction, but I'm telling you that if that in parentheses is equal to 0, which makes the top and bottom traction free, then the resultant on the left-hand side is also 0. Gerald? If that 2b plus sine 2b is equal to 0, it's going to make this resultant is also equal to 0. Gerald?
So, why can we say that is
Because we calculated the tractions. The problem is I didn't write the tractions here. If I wrote them, they look something big and it won't be anything that we can learn anything from. What is interesting is the resultant here. I have it here. If you want, I can show it to you so you can write it. I just didn't want to take the time to write them. But there, those values came directly from tractions, right? So here the tractions, if these guys are 0, the traction Tx itself will be 0. But on the left side, the tractions won't be 0. What will be 0 would be the integral. Thanks for the lively discussion, I liked it. So now that we have this, we are ready to interpret these results. This is pretty cool. Now, everything is 0. If you have traction free, the resultant here will be 0. Now, let's go back to this equation that I told you. So we don't have any real solution, but we have some imaginary, some complex solutions. So let's look at some of these solutions. So some of these solutions are, for example, you can see that B can be 2.1062 plus 1.125, or there are multiple solutions, of course, or larger values. So phi, the way it looks like, the way it looks like, it can be complex value. And if you think about the biharmonic equation, if you have everything is the derivatives are with respect to x and y. So if you have a complex valued function, do you agree that the real and imaginary parts both have to satisfy biharmonic equation? Because you have an I, which is not going to go away. For things to be equal to 0, the real part should be 0 plus I something equal to 0 equal to 0, without going to the details of that. So the wisdom in this statement is that we can actually, if we just look at the real part, this is actually going to be a solution. So if we look at the real part of B, this one, for example, the first one, which starts with 2, what does it look like? And then let's go back. It's like 2 something. Remember the number 2. Now look at the stress solutions again. Okay. If you look at the stress solution, you have an exponential term, e to the power of minus bx over a. And then this b, for example, can be 2. What is it telling you? What is happening? So you have something, some value which is not a function of x. Look in the stress solutions. But you have an exponential multiplied by that, which has a form like that, negative 2x over h. What does that tell you? What is happening with x? Exactly. So the solution. Now, if I would draw for you the solution, like one of the if I would draw for you for this level, for this b, this would be traction free. This is traction free. This is something, I don't know why. What I know is that the resultant is 0. And then I'm telling you that the solution that I have found is telling me that if you look at the stresses, they are exponentially decaying with x. Okay, why do I care about that? This problem, the resultant is 0. Can I sum it up with some other problem? Like imagine another beam, you have some moment on the left hand side, I can superimpose this problem over some other problem. The resultant is 0. You don't even know that you did that. Do I make sense? Okay. You all agree that exponential decay, everything is okay with that? Okay. Now, why this problem is important? Imagine the problem we solved last time. You have a beam, traction free, and you have a moment or something else happening at the left-hand boundary. Would you allow me to superimpose that problem with this problem? Why can't I do that? Because it is this is called a self-equilibrated. Yeah, I cannot pronounce that. Equilibrated. I have to always look at the word. Equilibrated problem. The resultant is 0. Everything is 0. So it can be inside of any problem that you are solving. It is it is there. You don't see it because the resultant is 0, and all you care about is the resultant. However, because of that, you have something which is exponentially decaying with x. This is the effect of boundary conditions. So a couple of weeks ago I told you the Saint-Bernard principle is good if you go far enough from a boundary. But I didn't tell you how far you can go. This is, for example, one analytical way which you can actually quantify how much a boundary can affect your solution at what distance. For example, if I look at e to the power of negative 2 and I go as much as h away, right, this solution reduces to about 1.5%. So the stress from 100 goes to 1.5%. So it tells you that if you go half the width of the beam, the effect of boundary is already 1%. So you have heard before, I'm sure, people told you if you load something, if you look at this thickness and go this way, from here on you can assume that the stress is uniform. How many have heard this before? All of you. But you never really yes, you can do finite simulations and you see some crazy things happening here and then things become nice. Yes, this is one way, but this is an analytical way.
So, is it like infinite sum of all of these, or is it just one?
So that's a good question. So this speed, if you take 5, it would be even faster decaying. So.
Eventually, it's not a good solution for the man because assumption of resultant being 0 is certainly not solve the problem along that line because there are cases where it's not linear. If you don't have a linear distribution there, you can't reduce the solution at the boundary.
Oh, this is not assuming any linearity. That was just an example to tell you that if the resultant is 0, doesn't mean that the traction is 0. This is definitely not linear. It can be it is actually something very crazy.
Yeah.
Depending on B, it's arbitrary.
Yeah, because some solutions, like in B, for example, if you are talking about the shares, you want to solve the share problems very, very closely.
Right.
So if you're going away from the edges, it's not going to be a very comprehensive solution.
Right, but this is not about that. This is just telling you that if you go far from the edges, you don't see the effect of boundary. But it makes the Saint-Venant principle more quantitative. Like really, what does it mean? Because always you heard if you go far enough, but what does it mean? But if you want to study the effect of boundary close to the boundary, you cannot use Saint-Venant principle anymore. You really have to consider the distribution and you really need to look exactly what's happened. Yeah, but this is a different thing. What I'm saying here is that I think this is Timoshenko, I think I told you before. Generally, if you look at it, how many of you have read like a Strengths of Materials from Timoshenko? And you can like read it at night, like enjoy, go to bed, right? He has a lot of elegant problems. It has. It's just that and this is, I think, a very elegant problem. And it was still manageable that I could solve it in the class for you. Because these solutions you cannot really write things in the class. But at the same time, I think the physical implications are quite fascinating, that you can actually see how fast the solution is decaying with X. So agree with me, please, that this is interesting problem, right? Yeah. So we have only a few minutes. So what I could do is you all okay with just staying a couple of minutes longer? Because I let you go 5 minutes early on Tuesday. Let me claim my 5 minutes. I understand. It's great. It's open to you. Don't worry. You can ask me questions. I told you there are not enough quizzes and every quiz has a lot of weight. You see?
So how many more pages are you going to do?
I like that and